The Earth is a dynamic canvas of ever-changing landscapes shaped by a multitude of geological processes. Among these processes, weathering plays a vital role in sculpting the planet's surface. Weathering, the gradual breakdown and alteration of rocks and minerals, is a creative force that has been at work for eons, shaping the diverse and captivating landscapes we see today. Welcome to Digital Learning. In this video, we will delve into the world of external land-forming processes, focusing on weathering, its agents, and the myriad factors that influence it. Weathering is a silent, patient artist that continuously reshapes the Earth's surface. It is the process by which rocks and minerals break down into smaller particles or change their composition due to various natural forces. Weathering relies on a set of tools known as agents to sculpt the Earth's surface. These agents are the dynamic forces that actively participate in the weathering process. The primary agents of weathering are water, wind, temperature changes, biological activity, and chemical agents. Water is one of the most influential weathering agents. Its ability to seep into cracks and crevices, dissolve minerals, and facilitate chemical reactions makes it a potent force in shaping landscapes. Water erosion and the formation of features like canyons, caves, and valleys are prime examples of its artistic influence. Wind, as another powerful weathering agent, carries abrasive particles that can wear down rocks and minerals over time. In arid regions, the abrasive action of wind-blown sand can sculpt unique landforms, such as desert arches and hoodoos. Temperature fluctuations are also important weathering agents. The expansion and contraction of rocks in response to temperature changes create internal stress, leading to the eventual breakdown of rocks. This is evident in the formation of spires and exfoliation sheets in rock formations. Biological activity, often overlooked, plays a subtle yet crucial role in weathering. Plants, microorganisms, and burrowing animals contribute to the physical and chemical breakdown of rocks. For instance, plant roots can penetrate and crack rocks as they seek nutrients, and microorganisms release organic acids that can chemically weather minerals. Chemical agents like acids produced through natural processes or pollution can accelerate the weathering of rocks. Acid rain, for example, can erode limestone monuments and damage buildings, showcasing the destructive potential of chemical agents. While weathering agents are the active tools, numerous factors influence the intensity and rate of weathering. These factors include climate, rock type, topography, and time. Climate has a profound impact on weathering processes. In areas with high rainfall and temperature fluctuations like tropical rainforests, weathering tends to be more rapid and aggressive. In contrast, arid and cold climates experience slower weathering due to the scarcity of water and temperature extremes. The type of rock or mineral also influences weathering. Rocks with varying mineral compositions react differently to weathering agents. For example, granite, composed mainly of quartz and feldspar, is more resistant to chemical weathering compared to limestone, which contains calcite and is vulnerable to dissolution. Topography and landform shape can affect weathering rates. Sloping landscapes tend to experience more rapid erosion as gravity aids the removal of weathered materials. Steeper slopes can lead to the creation of gullies and canyons over time, showcasing the powerful interplay between topography and weathering. Time as a weathering factor. Time is perhaps the most patient influencer of weathering. The longer a rock or mineral is exposed to weathering agents, the more pronounced the changes become. Over eons, weathering can transform towering mountains into rolling hills and jagged cliffs into smooth shorelines. The external land-forming process of weathering is a testament to the artistic prowess of nature. Through its silent, relentless work, it sculpts the diverse and captivating landscapes that grace our planet. Weathering employs a trio of techniques to work its magic on the planet's surface. These techniques encompass mechanical weathering, chemical weathering, and biological weathering, each contributing to the myriad landforms we behold. Mechanical weathering, often referred to as physical weathering, is the technique of fragmenting rocks without altering their chemical composition. This process relies on natural forces, including frost action, thermal expansion and contraction, exfoliation, and abrasion. Frost action, perhaps the most visually striking of these, occurs when water infiltrates the cracks and pores of rocks, freezes, and expands. The pressure exerted by this expansion can gradually split rocks apart, resulting in the formation of talus slopes or scree fields. Thermal expansion and contraction are another technique in mechanical weathering. When rocks are subjected to extreme temperature fluctuations, they expand when heated and contract when cooled. Over time, this expansion and contraction can weaken rocks, causing them to crack or spall. Such phenomena can be observed in regions with hot days and cold nights, where the surface layer of rocks undergoes continual expansion and contraction. Exfoliation, a process of mechanical weathering, involves the peeling away of outer layers of rock due to the reduction of pressure. This occurs when overlying rocks and materials are gradually eroded or removed, allowing the underlying rock to expand and fracture along concentric layers. The process is akin to the shedding of an outer shell, unveiling the fresher, unweathered rock beneath. Abrasion, the final technique of mechanical weathering, results from the physical grinding and wearing away of rocks by natural agents like wind, water, and ice. For instance, riverbed rocks are smoothed and rounded by the relentless action of flowing water, gradually wearing them down to form pebbles, cobbles, and ultimately sediment. Chemical weathering. Chemical weathering is the artist's palette for altering the chemical composition of rocks and minerals, creating a wide range of colors and textures. This technique relies on chemical reactions with agents like water, oxygen, carbon dioxide, and various acids. For example, in the presence of oxygen and water, iron reacts to form iron oxide, commonly known as rust. The gradual transformation of rocks, such as granite, to clay minerals through hydrolysis is another example of the chemical artistry of weathering. Carbonation, a specific process within chemical weathering, involves the reaction of carbon dioxide with water to form carbonic acid, which can dissolve minerals like calcite and limestone. Over time, this process can create karst landscapes with features such as sinkholes, caves, and underground river systems. Biological weathering introduces life into the artist's repertoire. Through the actions of plants, microorganisms, and burrowing animals, biological weathering influences the external landforming process. Plant roots, for example, penetrate rocks, causing physical disruption as they seek nutrients. Additionally, the release of organic acids by microorganisms can chemically weather minerals, softening and breaking down rocks. Even burrowing animals, such as earthworms, contribute to soil production and weathering by mixing and breaking down materials as they create tunnels and burrows. Weathering is more than just a geological process. It is the artist behind the masterpieces that define our planet's landscapes. Its significance is profound, as it is a fundamental step in the creation of soils, the development of ecosystems, and the formation of valuable mineral resources. Weathering also plays a crucial role in carbon cycling, regulating the Earth's climate, by removing carbon dioxide from the atmosphere and storing it in rocks and sediments. Moreover, it helps shape the environment, influencing the distribution of plants, animals, and human societies. While weathering meticulously crafts Earth's external features, mass wasting adds an element of unpredictability, transforming landscapes with sudden and powerful movements of materials. Mass wasting, also known as mass movement or mass wasting, occurs when rocks, soil, and debris dislodge and move downhill under the influence of gravity. The complex interplay of geological, climatic, and topographic factors determines the likelihood and intensity of mass wasting events. Several factors influence the occurrence and severity of mass wasting events. These include slope angle, rock and soil composition, climate, vegetation, human activities, and seismic activity. The steepness of a slope is a critical factor influencing mass wasting. Generally, steeper slopes are more prone to mass wasting because gravitational forces are stronger and materials are more likely to become dislodged. Even minor disturbances or additional weight can trigger mass wasting events on steep slopes. The type of rock and soil present on a slope greatly affects mass wasting. Loose, unconsolidated materials such as sand, silt, and clay are highly susceptible to mass wasting, while cohesive rocks with strong interlocking structures are more stable. The presence of fault lines, joints, and fractures in rocks can also contribute to increased instability. Climate. Climate plays a significant role in mass wasting events. Areas with heavy rainfall or snowmelt can saturate the soil and create lubrication between particles, making it easier for materials to slide or flow downhill. Drier regions are less prone to mass wasting, as the absence of moisture contributes to greater cohesion between particles. The presence or absence of vegetation on slopes can influence mass wasting. Plant roots help bind soil and rock particles together, enhancing stability. However, when vegetation is removed due to deforestation or construction, the risk of mass wasting increases. Human activities such as construction, mining, and excavation can disturb natural slopes, altering their stability and increasing the risk of mass wasting. Poorly designed infrastructure, improper drainage, and excessive excavation can exacerbate the problem. Seismic activity, including earthquakes, can trigger mass wasting events. The ground shaking caused by earthquakes can weaken slopes, leading to landslides and debris flows. The intensity of the earthquake and the geological characteristics of the area determine the level of risk. Mass wasting events vary in terms of speed and intensity. While some result in dramatic and rapid movements, others proceed at a slower pace, allowing for more predictability and potentially less damage. 3 common types of slow mass wasting are soil creep, solifluction, and rock creep. Soil creep is a gradual, almost imperceptible downhill movement of soil and loose rock particles. This type of mass wasting is the slowest and most common, occurring at a rate of just a few millimeters to a few centimeters per year. Soil particles expand and contract due to temperature fluctuations, pushing them downhill. The ongoing effects of gravity, combined with freeze-thaw cycles and wet-dry conditions, contribute to soil creep. Solifluction primarily occurs in permafrost regions, where the soil above the frozen ground becomes saturated with water. The upper layer, called the active layer, thaws during the warm season, but the permafrost below remains frozen. This creates a slippery boundary between the 2 layers, causing the saturated soil to slowly flow downslope. Solifluction results in the formation of characteristic lobes or terracets on hillsides. Rock creep is a slow, continuous movement of large rock fragments and boulders. Over time, the rocks shift downhill due to the relentless force of gravity, usually at rates of millimeters to centimeters per year. Factors like freeze-thaw cycles and seismic activity can contribute to rock creep, as they disturb the stability of rock blocks. The landscapes we cherish are not only the result of gradual weathering processes, but also the unpredictable, gravity-driven movements of mass wasting. In contrast to the slow and steady transformations of slow mass wasting, rapid mass wasting involves sudden and powerful movements of materials. These events can be devastating, occurring swiftly and with little warning. Common forms of rapid mass wasting include mudflows, earth flows, landslides, slumps, debris slides, rockfalls, avalanches, and rainwash. Mudflows, also known as debris flows or mudslides, are swift-moving mixtures of water, clay, silt, sand, and rocks. These viscous flows are often triggered by heavy rainfall or rapid snowmelt, causing the saturation of loose materials on steep slopes. Mudflows can be extremely destructive, burying everything in their path and posing significant threats to communities in hilly or mountainous regions. Earth flows are slower moving than mudflows, but still pose considerable risks. They involve the gradual downhill movement of saturated soil, typically in response to heavy rainfall. Earth flows can be particularly dangerous when they affect populated areas, causing property damage and potentially endangering lives. Landslides are among the most well-known forms of rapid mass wasting. These occur when rocks, soil, or debris detach from a slope and descend rapidly. Landslides can be triggered by various factors, including heavy rain, earthquakes, volcanic eruptions, and human activities. The results can be catastrophic, causing damage to infrastructure and threatening human lives. Slumps are characterized by the downward and outward movement of a mass of rock, soil, and debris along a curved surface. These movements occur when the materials at the base of a slope become saturated, leading to the loss of support and instability. Slumps can lead to the formation of scarps and can significantly disrupt the landscape. Debris slides involve the rapid descent of a mass of rock, soil, and debris down a slope. They differ from landslides in that they are typically more chaotic, with materials mixed haphazardly. These events can be triggered by heavy rainfall and often result in the burial of roads, houses, and vegetation. Rock slides are events where large rock masses detach and tumble downhill, often due to factors like seismic activity or heavy precipitation. These events can be highly destructive, especially in steep mountainous areas where large rocks gain momentum and can travel great distances. Rockfalls are characterized by individual rocks or boulders breaking free from cliffs or steep slopes and tumbling to the base. They can be triggered by frost action, water infiltration, and earthquakes, posing risks to anyone present below. Avalanches occur in snowy, mountainous regions and involve the sudden release of snow, ice, and debris down steep slopes. These events can be triggered by factors such as heavy snowfall, rapid temperature changes, or human activities. Avalanches can be deadly, burying people and structures under thick blankets of snow. Rainwash is the movement of surface materials, typically in hilly or mountainous regions, caused by heavy rainfall. While not as destructive as landslides or debris flows, rainwash can erode topsoil and disrupt landscapes. The consequences of mass wasting can have a profound impact on both the physical and human environments. Physically, mass wasting events can result in the creation of new landforms, the erosion of landscapes, and the burial of natural features. In the aftermath of mass wasting, scars on hillsides, terraces, and altered drainage patterns may emerge. On the human front, the effects can be far more devastating. Mass wasting poses immediate risks to human lives, leading to fatalities and injuries. It can also cause extensive property damage, destroying homes, infrastructure, and transportation routes. Communities in hilly or mountainous regions are particularly vulnerable to these events, often necessitating relocation or the implementation of protective measures such as retaining walls and slope stabilization. Furthermore, the impacts of mass wasting extend to the environment as a whole. Increased sedimentation in rivers and water bodies can harm aquatic ecosystems and water quality. Vegetation may be stripped away, leading to soil erosion and potentially affecting biodiversity. The potential for long-term environmental disruption and recovery is a critical consideration when assessing the impact of mass wasting events. In summary, weathering and mass wasting are integral components of Earth's dynamic and ever-evolving landscape. Weathering, with its patient and subtle alterations, sculpts the surface of our planet over geological timescales, contributing to the rich diversity of landforms we witness today. Mass wasting, on the other hand, adds a sense of unpredictability, with sudden and powerful movements of materials reshaping landscapes rapidly and sometimes dramatically. Both processes, while distinct in their mechanisms and speeds, work together to craft the intricate tapestry of Earth's physical features, from serene valleys and rolling hills to steep cliffs and breathtaking canyons. Understanding these natural forces is vital for the sustainable management of our environment and the safety of communities living in vulnerable areas. With that said, thanks for watching, and until next time.